pattern. Let's see. Okay. What else? The next thing is yep. Have to observe that and this one too. Ôi. Okay. Yes. I'm going to observe the stimulant right here. And yes, and this one too. Oh no. Take a look at the Zoom to YouTube channel. The channel. Where is the Zoom? What is that? Zoom. This one is Zoom. And let's take a look at that. Okay. And okay, ใช้สิ่งมาแล้วนะครับ Okay. What else? This one too. It's need to open this one. Where is the steam lab? Where is that? Okay, you now observe this one right same. Yes, same. Okay, this one. You have to look for your channel, right? This one, and that's it. And another two. Another two right here. Oh, writing. Yeah, also there. It is the suffering. And look at the Steam Lab right here. Yes, the Steam Lab. And this one, this is the OBSNo2. That's the okay มาแล้วครับ and we're gonna look at the zoom to YouTube, right? Oh, I don't know. Yes, then I have to throw away the file from this one. File มาที่ okay, own file, and what is that? There's nothing more, only two here. Okay. So do it. Line and 7, right? In airdrop, we're gonna throw away this one to iPad. Okay, to iPad, and that I to my iPad and to Suankularb to chapter 7 session. I said so. Okay. I hope that we okay, and we close this one. Import and okay. Good afternoon. We will have the new lecture note, which is longer than before, and chapter 7 here, right? Yes. Okay, today it's the M604 02.02.2022. Okay, and we open another file so that chapter 7. Yes, this one. Okay. Good afternoon, everybody. Welcome you to SCI33206. I hope that you can hear well. Where is the last time for us in M604 เราถึงไหนกันครับขอเช็คนิดนึงwhere is that? No, this one. To 604, the 25th lecture, good note. Right here, and มีใครจำได้ไหมครับว่าเราถึงตรงไหนกันQ helium. Okay, this one, right? 28. Nuclear fission is the next thing for us. Okay. Yes, we arrived somehow at the nuclear fission. Nuclear reaction we have seen already. We are gonna consider the nuclear fission, right? Yes. Okay. On page 94, 94 here. Okay. Yes, nuclear fission is the decay process. You have seen the beta, alpha decay, beta decay, and gamma decay, right? Yes, we are gonna consider the man-made, human-made nuclear reaction process, and that's the nuclear. It's called nuclear fission, right? Nuclear fission is the result from unstable nuclei that are split into two fragments instead of emitting alpha or beta particle. In that reaction, the total mass of the product usually is less than the original mass of the heavy nucleus because the heavy nucleus is not stable, and it tries to decompose into smaller nuclei, and the smaller nuclei would have better binding energy, better binding energy per nucleon. So the better binding energy per nucleon the nucleus has, so the less the mass that nucleus is going to have. And that's the reason why the outcome mass, even of two nuclei or two fragments, the summation of both would be less than the original big nucleus. And what is the result of the mass difference? The mass difference will be transformed into the kinetic energy, which is what you may have seen before, right? Yeah, the nuclei, the big nuclei, as you know, they are not stable at all. So when the time goes by, they are trying to have more stable status, and nuclear fission is one of the result of those unstable nuclei. Okay. The nuclear fission, nuclear, it's a fission, it's a decomposition of the big nuclei was discovered in 1939 by Otto Hahn and Fritz Strassmann. They bombard, bombard is bombard means that you try to accelerate a particle by any technique, and the high speed particle will hit the big nucleus or the big nuclei, and yeah, you will get something as the result. Okay, in this case they use neutrons. Okay, neutron is denoted by 10N. Okay, number of nucleon is 1, and number of proton is 0, and that's the behavior of, that's the property of neutron, right? Okay, the isotope or the element that is quite well known is uranium-235, which is an isotope of the uranium. Uranium has 236, 238, and so on. Okay, in this process, they accelerate the neutron, and the high-speed neutron hits the nuclei of the uranium-235. Because uranium-235 is not stable, and once it absorbs one more neutron, of course, the number of nucleons should be greater than that before by 1, right? And the number of protons would remain the same, 92. Okay, and it has a star here because the neutron doesn't have zero energy, it has also energy. So the nucleon, the nucleus here will be unstable. Okay, it has vibration because this one goes with high speed, And once the time goes by for a moment, this one will be decomposed into two fragments. Okay, they use the word fragments, mean two daughter nuclei. Okay, and the remaining thing will be a number of neutrons. Okay, you will get neutron again at the output, and not only single neutron as at the beginning. You have several a number which is denoted by capital N with subscript N. Okay, this one can be 2, 3, 4, 5. Okay, this one number of neutrons. Uranium-236 is the intermediate state that lasts only 10 to negative 12. Okay, it's what is it? Picosecond, right? Yeah, around picosecond, which very short. Okay, it lasts very short. Okay, short time. And yeah, you will have X and Y as the daughter nuclei, that the result from splitting the 236 uranium with this vibration. Okay, and the process, if you cannot completely understand 87, you can take a look at this figure. Here is the neutron, and it hits the uranium-235, right? The isotope 235 of the 235 isotope of uranium, and after that, of course, it has one more neutron. It's going to be uranium-236, but there is some shape behind uranium-236 because the neutron came with high speed with kinetic energy. The kinetic energy will be absorbed to this nucleus, the 236 uranium, and it gets vibration. Okay, it vibrates, and once it vibrates more and more, okay, they are gonna try to be stretched. Okay, they will state itself to be like this, and when the time goes by, those two sides will be finally split into two components, X and Y, like this. And apart from that, the neutron that stay inside this extended nucleus will be also separated from the fragments X and fragment Y. Okay, it's like this one. There are 3 neutrons. Okay, that get out of the fragment X and Y. Okay, and that's the single cycle of the nuclear fission for 235 uranium. Okay, this neutron can go to the next cycle. If you have uranium-235 around here, it's going to hit uranium-235 again, and uranium-235 will be split again into X and Y fragment. Okay, we go to the detail of X and Y. You know, we don't have the element X and Y. X and Y are used as the unknown variable. Yes, what is X and Y actually? So it's hard to say what are X and Y because there are many choices for the nucleus to be split. Okay, for example, once they make when they observe the result, the probability of the nucleus X and nucleus Y that get out of from this process, there is no single pair. Okay, there are many pairs for X and Y. Okay, and the probability is shown like this. They plot it as the dots, the black dots here, and they use the interpolation in the yellow line. You can see is that A is the number of nucleons in that nucleus, right? And you can see the high probability during 80 to 100. Okay, any nucleus that has nucleon between 90 and 100 nucleon are the most possible outcome from the fragment X or the fragment Y. And another range, okay, for the fragments or X or fragment Y is the result from 134 to 144. So there is no single unique pair for the fragment X and Y. Okay, we go further. In the typical reaction of this type, what you can see here, one of the most favorable pair of this probability curve is the following. They have neutron and it hits uranium. Okay, of course, it's going to be uranium-236 for a while in picosecond, and after that, it's the unstable uranium will be decomposed into X and Y, and the X can turn out to be 141 and 56 Ba. Okay, 56 correspond to barium, but this barium, this isotope of barium has the nucleon, has the number of nucleon as 141. You can see that 141 lies in the range of 134 and 144, right? So 141 is in this range. That's why this is the most possible. This is one of the most possible pair of the fragment X and the fragment Y. Okay, barium. And another one is the Kr. What is that? It's better if I bring you to the periodic table. Okay, periodic table. Okay, here. Okay, barium and krypton, right? 56. What is 56? Here. Okay, barium is right here, and that one is the isotope 141, right? 141. Okay, the 141 isotope of barium, but it's not the typical barium, because the typical barium would be somehow 138. Okay, and the krypton is 100. Oh no, krypton is lighter. Krypton has 92 nucleon and 36 proton. Okay, this is an isotope of the krypton. And where is krypton? 36. 36 is right here. This is one of the inert gas, right? This is one of the inert gas, so they become stable, right? 92, right? 92, but this one is only 84. Okay, krypton is one of the stable elements because it is an inert gas, but barium may be decomposed later. Okay, yeah, this is one of the possible pair of the fragments X and Y. The barium 141 and the krypton 92 are fission fragments, okay, in this process, and you get the outcome. You get another group of outcome, which is 3 pieces, 3 particles of neutron. Okay, you just insert only one neutron, okay, with high kinetic energy, with high speed, it hits the uranium, but you get at the end 3 neutrons, and this one is going to move also with kinetic energy later. Okay, most reactor in operation today use uranium as fuel. Okay, so uranium-235 is one of the popular initial elements for the nuclear fission. Okay, and nuclear fission can be applied to several situations. For example, For example, in the peaceful way, okay, in the electric power plants, okay, in several developed countries. For example, in Germany, where I have done my PhD, okay, I have seen also the nuclear power plant there. But nowadays, they try to reduce the nuclear power plant because of the security reason. Okay, France has also nuclear power plants. Okay, let's talk about our story. Otherwise, we cannot finish. Okay, natural uranium contains. Okay, let's talk about the nature. In nature, uranium has several isotopes, and the 235 uranium, which is the popular one for nuclear fission process here, is only 0.7% of the whole uranium, and 99.3 is the uranium-238 isotope. Okay, that has 3 more nucleons. Okay, 3 more neutrons actually. What about uranium-238? Uranium-238 isotope can absorb also the neutrons, but it doesn't behave like uranium-235 with high enough probability for it to sustain. It cannot be used as the power electricity generation because okay, you can hit the uranium-238 and it will be decomposed into fragment X and Y, but the outcome of the neutron would not have enough kinetic energy. Once the outcome, the output neutrons do not have enough kinetic energy, they cannot hit another uranium-238. So the chain process in uranium-238 would not take place. But the neutrons from the uranium-235 would have enough kinetic energy, even exceeding amount of kinetic energy. Okay, they try to reduce the speed of neutron even. Okay, the kinetic energy from of the neutron from this uranium-235 is much higher than uranium-238. So the chain process in uranium-235 would take place, and we prefer that because we don't want to accelerate neutron every time to hit the uranium isotope. Otherwise, it's chaotic. Okay, it's too complicated. Okay, uranium-238 tends to absorb also neutron, but rather than being decomposed into fragment X and Y, it turns out to be neptunium or plutonium. So let's take a look at the neptunium and plutonium. Where is that? Okay, neptunium and what's that? Uranium, right? Uranium is here. Once you inject or insert the high kinetic energy neutron to uranium-238, the neutron will stay inside the nucleus of uranium-238, and it turns out to be neptunium, this element, and plutonium, this one. Okay, it doesn't be decomposed. It is not decomposed into fragment X and Y. Okay, it has a different behavior than the uranium-235. Okay, and that's the thing that happens in nature. So human cannot apply uranium-238, which is the main isotope in nature. We use the rare isotope of uranium. So if you take a look at the chain process of nuclear fission in for uranium-235, okay, you accelerate the neutron and it moves with high speed. It hits the nucleus of uranium-235, and the big nucleus is decomposed into barium 141 and krypton 92. And apart from this fragment section Y, we have three outcome as three output particles as the neutron. And the moving neutron with high speed will hit another uranium-235, okay, because you don't have only a single piece of uranium-235 nucleus, but there are several nuclei of uranium-235 around there. Okay, if you pick up uranium-235 for 1 gram, there is no single nucleus or nucleus of uranium-235. Okay, there are like million uranium-235, and the neutron with high speed will hit the next or the adjacent nuclei of uranium-235. It can be decomposed into another pair rather than barium and krypton. For example, xenon and SR, which is strontium. Okay, where is that? Strontium. Strontium is something close to barium is here, right? Krypton, where is that? Krypton is here. Is where is that? Oh no. Okay, strontium, where is that? Uh, 35 is what is that? It's strontium 38, right? 38. Oh, somewhere here. Here. Okay, it turns out to be strontium. Okay, this one, and even xenon. Okay, strontium and xenon 54. Okay, the big one. The big one is xenon. Okay, you can observe that one of the fragment lie in the inner nuclei, right? Xenon here, and strontium is right here. Okay, above barium. Okay, another possible pair of the daughter nuclei is, for example, Y and I, right? 53 and 39. What is that? Iode, okay, 53 and 39 is yttrium, like here, okay, close to strontium. Okay, and another pair is NB and SB, 41 and 51. 41 and 51. 51 is antimony, and 41 is what is that? It's neop. Okay, I have also never heard this one before. Okay, but there are many possible pairs of the fragments X and fragment Y, and of course, after the decomposition of the uranium to several pair of daughter nuclei, you will get another approximately 3 or 2.5 neutrons from the second round of the composition, and this neutron will hit again the uranium-235, and this is the chain process of the nuclear fission that happens to uranium-235. Okay, human doesn't need to accelerate the neutron anymore. Okay, it will do it will hit the uranium-235 automatically in the sequential way like this. Okay, and you will get the kinetic energy from daughter nuclei and the kinetic energy from neutron. Okay, once you get kinetic energy, you get heat. Once you get heat, you can boil the water, and you can put the steam to turbine, and you can rotate the generator. You get electricity from that. All right. And this is taken from another book. You start from this side, right? You accelerate neutron to hit uranium. You get like krypton and barium, and you get the outputs, which are a number of neutrons, and neutrons will hit the uranium again to the 5, and one of the neutron could also miss any nucleus. Okay, it just go with high speed, but it doesn't hit any nuclei of uranium 35. Sorry. In the second round of the composition, uranium 35 can be decomposed into another pair of daughter nuclei. Not only krypton and barium, it can be cesium and I don't know, RB. What is that? RB. What is the atomic number? 37. 37 RB. Okay, rubidium. Okay, this one here, rubidium and cesium 55. Okay, rubium and cesium. Okay, in the same column. Okay, that's a pair of fragment X and Y, and you get xenon and strontium. This is what we have already visited. You could get again cesium, rubidium, barium, krypton. Okay, the outcome for the second round of nuclear fission will be neutron, right? And neutrons will go with high speed with kinetic energy. It will hit the uranium-235. You get again cesium, rubidium. Okay, for example, you get at the end neutrons again. Okay, and it will go further to hit the uranium-235. That's the chain process for nuclear fission. You may get barium, krypton again. You may get rubidium, cesium. You may get xenon and strontium. Okay, this is the third round of nuclear fission, and it's going to be the fourth round of nuclear fission, and blah blah blah. Okay, and if you want to stop it, human has created some technique. We will see it later. The property of neutron absorption by a nucleus is much greater for lower energy, less than 1 eV neutron. Okay, the neutrons with too much energy, with too much kinetic energy, will not be so good. Okay, because these will not decompose the nuclei of uranium-35. Only the neutron with low speed, okay, not very high speed, which has the kinetic energy around about 1 electron volt. For the high energy neutron, it can have the kinetic energy on the order of 1 mega electron volt, but it's not useful. Okay, it will not decompose the nucleus of uranium-35. For uranium-235, the slow neutron are far more likely to cause fission than the fast neutron. So uranium-235 prefer the slow neutron. For the chain reaction to continue, neutron must be slowed down. Okay, if you are human, you want to control this process to take place all the time, because at the beginning the neutron will have very high kinetic energy. You have to reduce the speed of the neutron in each generation, in each round. So what is the technique for that? So human is clever, and they try to reduce the speed of the neutron by collision with nuclei in the surrounding material, but not the nuclei by uranium-235. Okay, we're going to use the different material, and that material is called moderator. Okay, moderator could be graphite, okay, which is made of carbon, or heavy water. You know, heavy water. It's not the water that is heavier than it's water that is done by the bigger isotope of hydrogen. You know, hydrogen has only a single proton in the nucleus, right? But we prefer the hydrogen-2,1. Let me write down. You have several isotopes, right? You have you have H11, right? This is hydrogen, or sometimes it's known as protium, okay, which is the word derived from proton, because we have only a single proton. We have another isotope of the hydrogen, which is, oh, sorry for that, which is 2,1, right? This is deuterium. Yes, it could be also written as H21, okay? And you have another one which is not stable. It is 3, it is 3,1Nt, and it can be also written as hydrogen 3,1. And this is what the last one is known as tritium, right? There are 3 isotopes for hydrogen. Okay, the heavy water is made of deuterium, okay, which has 1 more neutron in the nucleus of the hydrogen. This one has 2 neutron more in the nucleus of hydrogen. All right, yes, that's the technique human has made at the moment. Okay, the next one, yeah, moderator can be made of graphite or heavy water, but this is a special water. You could get deuterium from the sea and so on, right, on Earth. And the structure of the reactor core, okay, the room, the place where we have uranium-235 decomposition of this figure here, okay, we will keep all this process inside this area. And what happens then? What are the components inside? Okay, this is the shield. Okay, if this one is broken, okay, it will be dangerous to us, and you may have ever heard the sad situation, the accident in several countries, for example, in Japan, and so on, right? This is the most important thing, okay? The water to protect or to make the security. And nowadays, many countries try to avoid the nuclear fission power plant. And you have the fuel elements. This is the source of uranium-235, okay, the red one here. This is dangerous, okay. If any neutron hit your stick here, it can be exploded because of the high energy neutron, okay. Human try to control the process by putting the control lots, okay. If you don't want this one to be spread so much, you can see that if you start only from a single nucleus, you will have many exploration onto several nuclei. This will be explode like the nuclear weapon, the nuclear bomb, and so on. They use this process without any controlling process. Okay, they don't have control at all in the nuclear bomb, but in the nuclear power plant we need to control. Okay, reduce a little bit. Otherwise, the power plant is going to be explode. Okay, and yes, yeah, we need to control the amount of energy because it's expand quickly. We use this one, the control lot, and I don't know what is the color here. I don't know what it's like orange, right? If on your monitor, this one might be called the orange. Okay, the orange area here means moderator. Moderator is made of graphite or heavy water. You may put heavy water, which is the heavier isotope of the hydrogen. You can get heavy water from the sea and so on. You pour it into this area there. The neutron will pass through the heavy water and the speed of the neutron will be reduced. Okay, and that's the technique human used to control the nuclear fission process. Okay, yes, let's go further. Just you see where the moderator live, right? This is the moderator, and controller is used to control how much energy you want. Okay, if you pull it up, okay, the neutron will go easily to hit the fuel element, and you will get high energy. If you put it down, leave it down, it's gonna obstruct some neutron, okay, and the amount of uranium-235 explosion will not be so high. Okay, the reactor core contains the control lots. This is the reactor core, the room where we have nuclear fission. We have control lots, the gray one. We have, let me open another one, it's better. Right, it's on page 101. Right, human is quite clever. We have control lots, which is this one. Control lots here. We have fuel elements containing enriched fuel, which is the most popular one for enriched fuel is uranium-235. You can use also another isotope. It could be anything else. And moderating material, okay, for example, graphite or heavy water, are surrounded by a radiation shield. This one is the most important thing. Okay, the security of any electric power plants by using nuclear fission depends on this wall. Okay, if there are too much heat, too much energy inside this one can be destroyed, and when this one is destroyed, you will get the leak of heavy water. You get the big nuclei, which is not good because they are going to produce beta particle, alpha particle, or even gamma rays to human. And the rate of reaction is controlled by this one. Okay, controller. If you pull it up, withdrawing, pull it up, you will have high reaction rate. If you insert it or leave it down, you will have lower reaction rate. That's the way human use. Okay, the controller are often this one. Okay, the controller, the gray one, is usually made of cadmium. Where is cadmium? CD cadmium. Cadmium is that kind of metal, right? ใครหาเจอบ้างไหมครับ cadmium? Where is cadmium? CD cadmium. ผมเตรียมไว้ก่อนนะครับแต่ว่าลืมนะครับเพราะมีหลายธาตุwhere is cadmium? Here cadmium. Okay, the 48. There are 48 protons. Okay, the next one after silver. Okay, the next element to silver, that's cadmium. Okay, they use this element to be made of control lots. Okay, because once the neutron hit the cadmium nuclei, there will be no decomposition. Okay, it has no result at all to cadmium elements. Okay, because the nuclei of the cadmium absorb the neutron without any additional reaction. Okay, human has tried to choose any base element, and that one turns to be cadmium. In a nuclear power plant, the fission energy appears as the kinetic energy of the fission fragment. Okay, the main energy that we get from the electric power plants is the kinetic energy of this one. Okay, Krypton, Baryons, rubidium, cesium, and strontium, xenon, and so on. These are the daughter nuclei or the fragments. Okay. Okay. Now we arrive at the whole structure of the electric power plant that is used on Earth เรามีเวลาเท่าไหร่14ต้องเลิกอีกประมาณ30 นาที okay yes of course this is the reactor core, right? You have control of pull it up or push it leave it down, right? This is the reactor core, and we have moderator, okay, to reduce the speed of the neutron, and we let the nuclear fission process happen here, right? Take place here, and of course you will get the high energy, high temperature from the wall of this one, and the water here, we leave the water around this reactor core, but inside the reactor core we use the heavy water. Okay, outside the reactor you can use any water, the typical water, and the water here will absorb the heat, and the high temperature water will go up. They go to this one, to the pipe, and they go to the pipe and turn around and go to the pump. The pump will repel the water in this loop. Okay, this is the closest system. Okay, this water will not touch the water in this area. This area is called stream generator. Okay, because this is the high energy water in the stream process, the water here will get also the energy from it's called primary loop. Okay, the primary water, and the second loop or the second water, the second set of the water will be changed to stream, and the stream will go to this area. This area is called turbine room, and we have turbine here. We have the turbine is connected to the shaft. The shaft is connected to generator. It's like a motor, but the functionality is in the reverse way. It converts the torque, mechanical torque, to be electricity, and once it rotates, the magnetic field will cut the copper winding, and it will generate electricity. We transmit electricity to a human, to the home, to industrial sector, to any application. All right, but the steam with high temperature like 60 degrees Celsius on 600 degrees Celsius or 700 degrees Celsius will be cool a little bit down, and it will change its phase from the gas to be, it will be condensed actually to become the drop of water, and the drop of water will again be used for the next cycle, next loop of the water in this area. Okay, what is the reason why this can be changed, condensed to become water? They use another loop of water, okay, to bring the heat out. Okay, the heat from the steam here will be transferred, will be absorbed and transferred to throw away or for any other purpose. Okay, and the gas phase of this stream will be condensed to become water. Okay, that's the whole process. There are deuterium water, okay, heavy water, and the first loop water, the second loop water here, and the third loop of water. You can see electric power plant use a lot of water. Okay, now we move to another thing, nuclear fission, right? Fission reactions are always exergic. So this is the name of spatial process. You have to know what is that. It's the in physics we call exergic, right? Ergic means energy. Ergic comes from the word energy, because the fission fragment have greater binding energy. The daughter nuclei has greater binding energy per nucleon than the original nucleus. The total kinetic energy of the fission fragments is enormous. For example, 200 mega electron volt for uranium-235. Okay, and the typical amount of the energy released by fission of a single heavy radioactive atom is about 100 million times the energy released by the combustion of one molecule of the octane used in gasoline engine. Okay, if you burn the fossil fuel, right, with the same amount of mass, the same with only one molecule, not the same amount. One molecule from the fossil, okay, and you use only a single radioactive nucleus, you will get 100 million greater energy than one molecule of the fossil. So it's very, very, very dense energy actually. Okay, but the more precious energy, the more difficulty you have to control, right? Because it can be exploded easily during this at this generation, right? And now we arrive at the first example. If the disintegration energy Q per event is 208, and next one is the question is calculate the total energy released by 235 uranium isotope for 1 kilogram. Okay, if we use 1 kilogram of uranium-235, what is the total energy liberation we could get from 1 kilogram of uranium? Now we need to first determine the number of nuclei in number of nuclei of uranium-235 in 1 kilogram, right? And as we know, uranium-235 of 1 kilogram can be determined by the number of Avogadro number divided by 235 gram per mole, right? Because we are using uranium-235, so it's going to be 235 gram per mole. And because physics need to be considered in SI system, we're gonna convert the gram scale to kilogram, right? We need to divide this amount by 1,000. We have 0.235 instead of 235, and the value of the Avogadro number, the number of nuclei or the number of atoms, right, in chemistry. But for us in physics, in nuclear physics, we are gonna say it corresponds to nuclei, okay, because each atom has a single nucleus. So in 1 mole of uranium-235, there will be 6.022, I don't know, 25 million, almost 4 times of million. And after the division of this ratio in the calculator, you will get 2.5626 10 to 24. That's million 4 times. Okay, the number of nuclei per kilogram. Okay, you get something like this. Okay, and it's a very, very large amount. But for a single nuclei that is decomposed or disintegrated, we will get 208 mega electron volts. We have to multiply by 208 mega electron volt per nuclei. We get 5.3 times 10 to 26 mega electron volts per kilogram. Okay, yeah, from 1 kilogram of uranium-235, we get the energy like, oh, I don't know how to say, 100 million, 100 million 4 times. Okay, 5.3301 times that amount. Very, very large. Okay, and that's why the people prefer nuclear energy, because it's you can get very high amount of energy from a very tiny amount of fuel, which is uranium-235, only 1 kilogram. The next question is, how many kilograms of uranium-235 would be needed if we want to supply the energy consumption in the whole world? For example, if the whole world uses the energy by 4 times 10 to 20 joule. Okay, this is the amount of energy in the SI system, right? It's not in the nuclear physics scale. So yeah. We know that uranium-235 could provide 5.33 10 to 26 mega electron volt per kilogram, like this. And if you want a number, if you want to know the number of kilograms, you need to divide this one by, you need to divide the energy by this one. So 4 times 10 to 20 joule divided by the amount of energy per kilogram, and you will know the number of kilogram, right? Yes, but they have different units for the energy. In nuclear physics, we express the energy in terms of electron volt, but in SI system, they use the joule as the unit for the energy. So you just convert one of the thing to be of the same unit. For example, you may convert the mega electron volt to be joule. For example, 1 eV, 1 electron volt, is equal to 1.6 10 to negative 19, right? But we consider mega, right? So mega we should be divided by 1 million. So no, you have to multiply it by 1 million, right? Okay. For 1 mega electron volt, you have to multiply it by 1 million. So 1.602 times 10 raised to negative 19, which is the charge of electron, multiplied by 1 million, which is 10 raised to 6, is going to be 10 to negative 13. And once you multiply this and you divide the required energy, you will get the amount of kilogram, which is 4.7 approximately 4.7 million kilogram, or 4.7 thousand, or 4,684.5 tons. Okay, that's the amount of energy per day, right? Or annual, okay, per year. You have to burn or consume the uranium like 4,684.5 ton per year, okay, so that you can supply the whole world by this energy. But actually the electric power plant has some loss factor, okay. You cannot get 100% of the energy from the power plant. Okay, let's move to the second example. If each fission provides 200 mega electron volts, how much uranium has to undergo fission per unit time to provide 3,000 mega watts of thermal power? เดี๋ยวนะผมร้อนนะครับขออนุญาตลดแอร์นิดนึงครับ Okay, let's go further. And yeah, this one is a little bit more complicated than the previous example, because it's the rate of energy per time, right? It's the rate of energy, and if you want to supply 3,000 megawatts of thermal power, so how much uranium you have to make the fission process per time? Okay, this problem is quite similar to the previous problem. We need to know the number of uranium-235 nuclei. We need to know the uranium-235 nuclei per 1 kilogram, and the result is already there in 89. Okay, that's the Avogadro number divided by 235 gram per mole. Okay, it's 2.56 million photons. Okay, and yeah, we get yes, we will use we will start from the required amount of energy, which is 3,000 mega, right? This is million, this is 1,000, 10 to 3, 10 to 6, so it's 3 times 10 to 9 joule per second, right? The unit of watt is actually joule per second. And here is the number of uranium-235 per 1 kilogram. Okay, per mole, sorry, the number per 1 kilogram. The number of uranium-235 per kilogram, and here is the energy released by a single nucleus of uranium-235, which is 200 mega electron volt right here. Okay, yes, we leave the result of 89, which is 2.56 million photon nuclei per kilogram, and the amount of energy released by a single fission, and we divide to require amount of energy, and just you leave them in calculator, you will get somehow like 3.6539 10 to negative 5 kilogram per second. But 10 to negative 5 is hard for us to understand, right? We're gonna combine to kilogram a little bit. Kilogram means 1 raised to 3, right? 1,000, and this 1 raised to 3, and this 10 raised to 3, and this is 10 raised to negative 5. It's going to remain 10 to negative 2, right? And we move the decimal point to be here, so that it's going to be 10 to negative 3, which is milligram. So finally, it turns out to be 36.539 milligram per second. All right, and that's the result, the answer to this. So we finished the nuclear fission. Now we move to the next topic, which is nuclear fusion. Nuclear fusion is the reaction of 2 or more small light nuclei combined to form a larger nucleus. In the opposite way to nuclear fission. Okay, nuclear fission decomposes the big nuclei to be smaller nuclei, right? But nuclear fusion is the combination of lighter or smaller nuclei to become bigger nucleus. Okay, 2 or more light nuclei combine to form a heavier nucleus. This process is called nuclear fission. That's the topic of this one. Usually, the mass of the final nucleus is less than the sum of the masses of the original nuclei. So the outcome would have less mass than the original state or the initial state. There is the loss of mass, and of course, the mass difference will be transformed to energy released. Okay, and we will see some example that could take place. Human try to use nuclear fusion to generate energy on Earth, but it was not fully successful. It's not completely. It was not completely successful because this process requires extremely high energy, and we still do not have any device to sustain like million Kelvin and so on. Okay, 3 examples of energy liberating fusion reaction are in the following process. Okay, even we don't have the fusion on Earth, but human is clever. They can analyze the nuclear fission. They can analyze the nuclear fission on the sun. Okay, that take place every time at the sun. Okay, 2 protons denote. Okay, the proton is denoted by 1,1p, right? 2 proton denotes by 1,1p, or the hydrogen 1,1. Okay, combined to form a deuteron, right? You know deuteron, H21 and D21. A positron, which is denoted by E01, and beta 01. All right, and that's a positron. Okay, and the positron. Okay, electron neutrino denoted by V00 with subscript E. And of course, we have hydrogen 1,1, which is the proton, right? Hydrogen 1,1 and hydrogen 1,1, which is another proton. And here we got we get the outcome or the output as the deuterium. Okay, the bigger version of the hydrogen with 2 nucleon. 1 is proton and 1 is neutron, right? Yeah, because the proton turns out to be the proton turns out to be neutron, so it's going to release the positron. Okay, and the electron neutrino, so we get the balance 1 plus 1 equals to 1 plus 1 plus 0. 1 plus 1 is equal to 2 plus 0, 2 plus 0. Okay, there is balance above and below here. And from the reaction energy calculation, we have to find the mass difference between both sides, and usually the neutrino has very small amount of mass. We can neglect it. Once we neglect, we will get only the approximation. Okay, 2 times mass of the proton, because we have 2 particles of the proton here, or the hydrogen 1,1, and the mass of the deuteron and mass of the positron. Okay, the mass of the positron is equal to the mass of electron actually. So we get to M11H and minus M21D and minus M01 beta, which is the positron. And we need to multiply by 931.5 mega electron volt per atomic mass unit once we use the small m. Okay, if we use the capital M, we're gonna say this is c squared from the famous formula of Albert Einstein. Yeah, we leave the mass of the hydrogen nucleus here, 1.07825. Please don't leave the mass of the proton, which this is the mass of the mass of the whole atom of the hydrogen. And here is the mass of the deuteron. Okay, 2.014101 atomic mass unit. Mass of proton, which is very tiny because it corresponds to the mass of electron, is very small, and you multiply by 931.5 again. So you will get at the end the amount of energy released, because the energy turns out to be positive. So you accelerate the proton to hit the proton. Both have acceleration. They just join together with kinetic energy. But the outcome we here have the outcome here has 3 particles, and the mass difference is positive, and we get the released energy. It means that the kinetic energy of these 3 particles is greater than the kinetic energy of these 2 particles, because we get the energy difference like this. Okay, the proton will annihilate later with an electron. Okay, the positron here will combine with electron in the surrounding, and it's going to form two gamma rays. And yeah, if the whole process here is written together with one electron, is going to be D2101, which is the positron, and we get electron, right? The same result here, and we have electron in addition. And after that, the positron and the neutron, okay, particle and antiparticle will be combined together, and they will release the high energy photon, and that's denoted by gamma. And once we compute the energy from the mass difference here, because we don't have positron or electron anymore here, but we start from the mass of two hydrogen, and one electron is going to be reduced by only the deuterium, right? We leave the mass of hydrogen nucleus, electron, and the deuterium nucleus, and multiplied by 931.5, we get 1.9543 mega electron volt. You could see that we have much more, more energy than before, okay? And 1.9543 include the energy for this photon. Okay, the next process for this way is the hydrogen 1,1, okay, and a deuteron D21 will combine to with each other to form the light isotope of helium. Okay, smaller nuclei will form bigger nucleus. For example, the hydrogen will pick up the deuteron here, and it will form the bigger nucleus, and that's the hydrogen 32. Okay, hydrogen 32, because we have here 1 plus 2 is going to be 3, 1 plus 1 is going to be 2. All right, and it will provide the energy from the mass difference, right, in the typical way. We get mass of proton, mass of deuterium, mass of helium 32. Please note that helium has several isotopes. If you take a look at the table at the beginning, helium 32 is the light version of helium, right? Because this is the 32 helium isotope. This is the stable one, helium 42, which is the alpha particle, right? Okay. Yeah, we leave the mass of several particles into this formula. We get the energy for the photon and the light helium, which is helium 32 isotope. We get the energy on the order of 5.4931, okay, mega electron volt, which is again greater than this value. In the third process, could take place in two ways. The first way is the proton in that area will combine to the recently from helium 32, the light nucleus of helium, and yeah, proton and helium 32 will generate or produce helium 42, okay, which is the bigger version of helium, okay, and we get again a positron, okay. According to this process, helium 1 plus helium 32 will turn out to be helium 42, okay, and we get positron and photon too, right? Yeah, we get photon again, or gamma ray, and yeah, we could find the mass difference, and we multiply it with 931.5 megaelectron volt per atomic mass unit. We leave every mass values, and we get the energy at the outcome as 19.284 mega electron volt. This is a very high amount of energy, so it's going to be distributed to positron or the alpha particle, or even to the photon or the gamma ray. The next possible way is the two light heliums, helium-32, just combine to each other to produce helium-42 and 2 protons. Okay, this is what the scientists expected that could take place on the sun. Okay, the light version of helium-32 combine to each other to produce helium-42 and hydrogen 1,1 and another piece of hydrogen 1,1. Please note that 3 plus 3 becomes 4 plus 1 and 1, and 2 plus 2 becomes 2 plus 1 and plus 1. So you could have the mass difference again, 2 times of helium-32, 2 times of the light helium, 1 particle of the typical helium or the alpha particle, and we get the proton, 2 particles of proton. You leave the value of helium-32 mass, you leave the value of helium-42 mass or the alpha particle, and you substitute the value of the mass of hydrogen, typical hydrogen. You get the released energy by 12.859 mega electron volts. Okay, and that's the third or the last process in nuclear fusion that could take place on the sun. But the time is over. Right now, we need to stop our lecture. See you on Friday. We are gonna continue our lecture right here on page 113. Okay, M604 here at 02.02. If you have any question, just let me know. If not, then see you on Friday. Bye bye ครับ สวัสดีครับ
wait, no. Oh. Oh.
โอเคเราวิพลมาแล้วครับโอเค Okay, good afternoon everybody. Welcome you to SCI. This is the section for M605, right? Yeah. ก่อนนะครับพิมพ์มาแล้วนะครับพวิทย์นะครับนะเท่าที่ผมจำได้นะน่าจะเป็นชื่อ605แล้วนะครับโอเคokay what else for M605 there's nothing right yeahแล้วผมขอมอนิเตอร์ผ่านมือถือนิดนึงนะครับSC no SCI33206 today is yes which one do you want to see? Oh, that one, this one, Steam Lab. Okay, Steam Lab. All right. Okay. Because you have or you are now reading the M604 so much. Okay, and I think this week we may not have the homework at all because we are not dealing with any numerical example. We will talk about only the details in text and so on. Okay, let's start with our lecture. You have finished it at this point, right? The electromagnetic force, right? It's a long range force that decrease with distance square, okay, inverse square rule. The next one is the short length nuclear force, and it's known as the weak force. Okay, we have considered two forces, right? The strong force and the electromagnetic force, and yeah, they are both are quite strong. Okay, electromagnetic force is 100 less than strong force. Okay, it's short. No, it's a long range force. Like the strong force of the nuclear force, which is very, very short, 10 to negative 15. Okay. Okay, photon is the particle that is used to mediate electromagnetic force. We will talk about that later. Now we move to the weak force that may not be quite easy, or we may not be familiar with the weak force. Okay, what is that? The weak force will be exhibit in the instability of certain nuclei. It is involved in the mechanism of the beta decay. Its strength is only 1 million 1 by 1 million. That of the strong force are very small. Okay, and the gravitational that's the weak force. Now we consider the fourth one, which is the gravitational force, is the long range. The strength of the gravitational force is around it's 10 to negative 43. Okay, very small compared to the strong force. And although this gravitational force is the force that used to explain many things about planets, that holds or keep a planet, star, and galaxies to stay together, its effect on elementary particle could be neglected. Okay, because it's very small. Okay, the effect from gravitational force is very small, and it can be neglected for elementary particles, because now we are talking about the particle in physics, right? Okay, gravitational force is by far the weakest of all the fundamental forces, the four fundamental forces. And modern physics often describe the force between particles in terms of once we finish all these four forces, physicists try to explain these four forces by using the idea of particle exchange. Okay, in terms of the action of few particles or quanta, and the name of few particles or quanta will be different for each force. Forces between two particles are conveyed by an exchange of few quanta. Okay, quanta is the plural form of the quantum word. All right, and let's move to the next one. This process is analogous to the covalent bond. If you have ever studied chemistry before, right? There are many kinds of bond in chemistry. One of the bond that is well known is covalent bond, right? In chemistry, the covalent bond is the case when two atoms exchange their electrons or share their electrons, right? It's the same thing here for the two particles in the space. Okay, in the universe. Okay, they change the field quanta, and that's why they have force to each other. All right. Okay, let's make the summarization to the four fundamental forces. Okay, it's taken from the book number 1 and number 4, and yes, we have four forces: gravitational force, electromagnetic force, and weak force, and strong force that lies in the nucleus, right? And the first property is relative strength. Okay, in the approximation way, because some of the forces are not well known. Okay, if we let the strong force to become the reference, okay, let's say it's number 1, but it's not 1 Newton. Okay, it could be million Newton, but we unified as number 1. Okay, let's say that's number 1. We compare the remaining 3 forces to the strong force, so that's why it's 1. Because strong force is compared to itself, it's going to be only number 1. The weak force will be somehow 1 by million to 1 by million, compared to the strong force is really light. Electromagnetic force is around 1 by 100 compared to the strong force, and gravitational force is very tight, very tiny, 10 to negative 43 to 10 to negative 38. Oh, is very, very small. It can be neglected in this case. All right. Let's take a look at the aspect of range that could take place from all these 4 fundamental forces. Okay, the range for the gravitational force is infinite. Okay, you can get the gravitational force when you are very extremely far away from the source of that object or that particle. The electromagnetic force too. Okay, you could still get electromagnetic wave or the electromagnetic force once you are very, very far from the source of electromagnetic wave. Okay, but both of these both forces will have less and less force, less amount of force once you are far away. Okay, and the rule to determine the amount of force is the inverse of the distance square. Okay, 1 by r square. Okay, that's the distance square inverse rule. Okay, so let's talk about a weak force. Weak force will take place when you are very, very close to each other, 10 to negative 18 meter. Okay, this is not relation. It's not relative. It's the actual distance in SI unit scale in meter. 10 to negative 18. Okay, 1 by 1000 femtometer or Fermi. Okay, and strong force will take place once you are very close on the order of 1 Fermi or 1 femtometer, 10 to negative 15. Okay, let's talk about whether the force could be repulsive force or attractive force. Okay, they want to join 2 particles together or they want to repel 2 particles from each other. For the gravitational force, it is only attractive force. Okay, there is no repulsive force for the gravitational force. If you are close to any planet, you will be attracted to that star. For electromagnetic force, you can get either a repulsive force or attractive force from electromagnetic wave. And what about weak force? Weak force could deliver both repulsive and attractive force to you. What about strong force? Of course, strong force could be repulsive force and also attractive force if the nucleon have the same charge. Okay, and it could be repulsive when the nucleons have the same kind of charge, but it's not charge because it's going to be the Coulomb force. Carrier particle, what is the carrier particle for each 4 fundamental force? For the gravity, the physicists believe that there should be a particle which is known as graviton, but no one could prove this in experiment right now. And regarding the electromagnetic force, of course, we know that photon is the field quanta, okay, the amount of energy that carry electromagnetic force. Okay, photon is known for us, gamma ray and so on. What about weak force? Weak force used W plus boson, W minus boson, okay, and Z0 boson to be its carriers. Okay, there are 3 types of particles to carry the weak force. And what about strong force? Strong force used gluon to be its carrier particle. Okay, and what about the status of the carrier for these 4 forces? Okay, at the moment, graviton is expected to be found, right? It's in it's conjectured. Okay, it is expected to for human to find. And electromagnetic force, of course, photon is is verified. The human has already observed, has been already be able to observe the photon. What about the weak force? Of course, W plus boson, W minus boson, or Z0 boson are already observed by human because we have already discovered it. And what about a strong force? The gluon is still not verified, but the scientists or the physicists believe that there should be a particle which is known as gluon. Okay, this is still conjectured. Okay, it's still in expectation for human to find. Okay, let's take a look at quarks. Right, quarks, leptons. Let's talk about a fun, elementary particle for us to have to build up the standard model. Quarks, leptons. Electron is an example of leptons, and the particle that convey force, for example, a photon, are now thought to be the truly fundamental particles. Okay, there are several hundreds particles that human could find, but only these three: quarks, leptons, and the particle that convey force, okay, which is like this one, carrier, are considered as the truly fundamental particles. Let's take a look at the basic theory of physics particles. One of the things is the Dirac's theory. He said that for every particle, there is an antiparticle with the same mass as the particle, but opposite charge or opposite number of something. An antiparticle is usually designated by a bar over the symbol for that particle, except for the positron. The positron used the positive side on the superscript at the right hand side instead of the bar, because we used electron notation, and if this is the negative one, it means the electron one. Okay, among the abstractions are the photon, the neutral pion, denoted by pi with pi less to 0. Okay, the neutral version of pion are the particles that have no antiparticles, because they are already the antiparticles to them. Okay, so they don't have antiparticles. Okay, there are two exceptional particles, photon and neutral pion. Okay, apart from that, every particle should have its own antiparticle. When a particle meets its antiparticle, what will take place then? And you may have already seen in the nuclear fusion, when the positron meets the electron, they are gonna combine to each other, and the word for combination is known as annihilation, right? Both particles will be annihilated, will be combined to each other, and it will give you high energy photon, okay, gamma, or high energy photon. In order to see our particles in physics, we need to classify the particles in terms of their interaction. We will also distinguish them or classify them between bosons, which always have 0 or integer spin, and fermions, which have half integer spin. Okay, these two things might be already considered in the previous chapter, but we will see it again here. Fermions obey the exclusion principle by Paulie, right? Wolfgang Paulie, but boson will follow the Bose statistical probability. Okay, in yes, let's take a look at the standard model for us that might have been already seen, that you may have already seen previously in in the previous chapter, right? Let me open again. Okay, and as you can see, quark, right? Quark is here. Quarks, leptons. Okay, from these quarks, leptons. Okay, quarks right here. Okay, the violet one. Leptons. Okay, lepton, the green one, and where is that? Oh, the particle that convey forces, which are known here as bosons. Okay, are considered as the truly fundamental particles. Okay, every bigger particle could be formed up by using these three groups. Okay, three types of particles. That's the first text. The next one is that Dirac said every particle should have its own antiparticle. You could see here the up quark has its own anti-up particle. Sham quark has its own anti-sham particle, which is denoted by bar above that variable. And you could see here the mass is the same. Mass is negative 2.2 mega electron volt. The mass is the same. All right. Not negative, it's approximation. Sorry. It's not negative, it's approximation. Okay. And yeah, it's better. And top quark had its own anti-top particle, which is denoted by bar above the letter T. The dark quark has its own anti-down particle with the same mass, different charge, negative 1/3 charge of the electron. The anti-down has a positive charge of electron. Okay, and the strange quark has same mass 96, the 96 here to anti-strange particle, but this one has negative 1/3. Okay, and negative 1/3 in bottom quark. Bottom quark has its own anti-bottom particles too, which has the same mass as the bottom quark particle, and the difference is only the charge. For the up quark, it has the charge of 2/3 of electron, but the anti-up it has the negative charge to the up quark particle. Okay, you could see that the charge is opposite to the original particle. Okay, and for the electron has -1 because 1e is the quantity of the electron charge, but it's negative, right? Because electron has a negative charge. For the positron has the same mass, 0.511 megaelectron volt per c square, as same as the electron, but the charge for the positron is +1. Okay, muon is a bigger version of electron. You could see here the mass is 105 megaelectron volt. This one is 2.5. It's now 227 bigger than the electron, and the tau lepton or the tau particle is even bigger than the muon, much bigger than electron. But the bigger particles here are not stable. They are gonna decay finally to become electron. All right, tau also has its own anti-tau. Okay, so how does the human discover this particle? Okay, they build up the giant sides of accelerator. Okay, when you accelerate the particle and it hits a nucleon and so on, or a nucleus, you would get a bigger nucleus, okay, because of the high energy amounts from the acceleration, and that's why you get the big particle here. But the big particle is not stable. They're gonna fall down, okay, or decay into the middle version and into finally the smallest version, which is electron. But at least humans know that there are muon and tau. So what is the benefit for human to do this experiment? Because we would be able to explain how the universe is forming up. Okay, once you know the behavior of several fundamental particles, you could also understand how the universe is formulated, is originated, and you could expect what is going to happen in the future. Okay, and that's the effort by human to understand the universe by exploring the fundamental particles in the universe like this. Okay, that's the negative version, right? The negative version of the electron. You could see that somehow here the tau lepton has the mass of 1.7768. Okay, it's comparable to the charm quark. Okay, it's in the same scale, the same level as the charm quark. It's big enough. Why don't we consider tau lepton to become quark? Any people, any person who could give me the answer? ครับทำไมถามภาษาไทย ถ้าคุณดูดีๆนะครับว่าเทาเนี่ยแมสของมันกิกะอิเล็กตรอนโวลต์ per c square ครับมันก็ใหญ่กว่าชามควาร์กอีกนะ 1.28 กิกะใหญ่กว่าอัพควาร์กดาวควาร์กด้วยซ้ำไปถามว่าทำไมเขาไม่แบ่งเทาไปเป็นควาร์กไม่จับเทาให้เป็นควาร์กไปเลยเพราะว่าแมสมันเท่ากันแล้วมันใหญ่กว่าอัพควาร์กดาวควาร์กด้วยซ้ำนะครับ What is the reason why we don't classify tau into quark category or even the anti-tau? What is the reason? มีใครตอบได้ไหมครับว่าทำไมเราไม่จัดเทาเล็ปตอนหรือว่าเทาพาร์ติเคิลเนี่ยให้อยู่ในกลุ่มของให้อยู่ในกลุ่มของเขาเรียกว่าไงให้อยู่ในกลุ่มของพวกควาร์กทั้งที่แมสมันก็ใหญ่แล้วนะ What is the reason? The reason is that because tau particle or tau lepton that's not involved with the strong interaction in the nuclear force, okay, in the strong force. So even it's big enough, it has giant mass, but it doesn't belong to the quark category because it's not involved with the strong interaction in the strong force. Okay, it's behave in the same way as electron. Okay, คุณจะพบว่าอิเล็กตรอนมันไม่เกี่ยวกับปฏิกิริยานิวเคลียร์เลยเนาะนะครับพวกอัพควาร์กดาวควาร์กนั่นแหละที่มันยุ่งอยู่ในโปรตอนนะครับนั่นคือทำให้เกิดพลังงานในนิวเคลียร์ฟิวชั่นนะครับโอเคไหมโอเคyeah you know everything about the electron, muon, and tau, right? There is another group in this lepton which is called neutrino, right? Electron had its own electron neutrino. The mass is very, very light. What is neutrino? Neutrino has no charge, but the spin number is the same as electron. All right, and you could see that all of these, whether it's violet or green, all of these has all of these have the spin number as 1/2, okay, one half, okay, and but the mass is different, and the charge is also different. Electron neutrino has no charge, it's zero charge. Muon has also its own muon neutrino. The mass is a little bit is much bigger than electron neutrino. The tau has its own tau neutrino, is even bigger or greater than the mass by muon neutrino. And of course, once we have the direct particle, we have the antiparticle here, electron antineutrino, muon antineutrino, and tau antineutrino. You may observe that the mass is the same, the charge is the same because it's 0, and the spin number is the same for both. But what is the reason why they have antiparticle? They will have the lepton number in a different values, okay? They will have different values of the lepton number, but it's not shown here. And that's why we still consider electron antineutrino as the antiparticle to electron neutrino, and muon antineutrino as the antiparticle to muon neutrino. Tau antineutrino as the antiparticle to tau neutrino. All right. Now we move to the right hand side, which is the force exchange or force carrier particle. It's gluon, which is not confirmed in the. It's not confirmed in the experiment. Photon is already found, right? It's confirmed. W or Z boson here already confirmed, and Higgs boson is still is already known, right? It's already confirmed. The charge for these particles usually is 0, remains 0, except for W plus boson and W minus boson. It has one full charge to that electron, and negative one to that electron, and the mass of W boson are the same. It's a big one, right? 80 giga electron volt per c². Z0 boson 2, it's even bigger, 91.19 giga electron volt per c². Photon has no mass, has no charge, but spin number is 1. Okay, gluon has no mass, no charge, spin number as number 1. Higgs boson is a big particle, 124.97 giga electron volt per c². No charge, no spin number at all. It's different. Okay, this is the scalar boson because it has no spin number, and this is classified as the vector boson because the spin number is 1. All right, these 6 particles are the carrier particles to combine all those quarks or even the leptons. All right, this is the standard model you may have already seen, right? Okay, this group, which is known as the fermions, right, whether it's quark or leptons, will follow the Paulie exclusion principle. What is the Paulie exclusion principle? It means the particles cannot have all quantum numbers at the same time. Okay, these particles cannot have the same state at the same time. Same state means the same quantum number, right? Not only electron, but every fermion here, whether electron, muon, tau, quark down, quark straight, quark, sham, quark top, quark bottom, or antiparticles, or their antiparticles, cannot have the same quantum numbers. They cannot locate at the same position, actually. Okay, that's the fermion. But the boson could take place at the same location at the same time, even there are different particles. All right, that's the difference between boson and antineutrino. And the way you want to find the location of the boson could be found by the Boson probability theory, okay, which is beyond our level. All right, let's move to the next one, which is more visual. I'm sorry, this figure is taken from the book in German. Okay, it's taken from the German book, so you could see here electron. Okay, they use K instead of C. Yeah, this is the size of electron. It's less than, it's around 1 by 1000 femtometer, and electron move around the nucleus, right? And yeah, they turn around in the orbits of its own circle. And yeah, the size of the atom is around angstrom, right? 10 to negative 10 meter. It's 0.1 nanometer, you can say that. And if we take a look at the inside, the heart or center of the atom, and that's the subject for this chapter, it's called, sorry, this is the German word, it's called Kern, okay, Kern, which means nucleus for us, okay. This is the German word, Kern. It means nucleus for us, and the size of the nucleus is around femtometer, for example, 10 to negative 14, or 10 times 10 femtometer, or 6 femtometer. It depends on the size, how big is your nucleus or nuclei. Okay, Kern means nucleus, but this word is German word, okay. And of course, the nucleus is the location where we form nucleon to stay together, right? And nucleons mean it could be proton or neutron, right? And the size of the proton should be less than the nucleus, right? Size of proton is around 1 femtometer, right? 10 to negative 15. But you know that inside proton or neutron we have quark, right? Which is what you have seen here. Proton is composed of 2 up quarks and a single or 1 dark quark. Neutron contains 2 dark quarks and 1 up quark. So there are three quarks inside proton or neutron. But the size of the quark itself is less than the nucleon, proton or neutron. It has the same size as electron, 10 to negative 18 meter. Okay, this is the comparison of the size of electron, atom, nucleus, nucleon, and quark, right? So you could compare from this standard table for elementary particles. So we will consider more particles apart from elementary particles. This is the basic particle. Okay, now we move to the story about bigger particles, but before that, let's get into the detail of quarks. Of course, up quark has the charge compared to electron, right? In terms of E, as 2 by 3 is a positive 2 by 3, 2/3 actually, and speed number 1 by 2. All the quarks, all fermion has the half spin number, and the baryon number, you will see baryon later, it's denoted by 1 by 3. All of these belong to also the baryon number. It's 1 by 3. Strangeness, because up quark is not a strange quark, it has 0, It's not charm quark, it has 0 charm number. It's not bottom quark, it has 0 bottomness. Topness, it has also no value because it's up quark, it's not top quark. The down quark has the negative 1/3 compared to electron charge. The spin number is still 1/2 or 1/2, and 1/3 for baryon number. Strain rate is 0 because it's not strained quark, and 0 charm, 0 bottom, 0 topnet because down quark is not related to charm bottom at all. The strained quark has 1/3, negative 1/3, and 1/2 spin number, 1/3 baryon number. Now, when we consider the strain rate or strain number, it has -1. Okay, -1 strain rate. The charm quark, okay, 0 charm, 0 bottomness, 0 topness. The charm quark has the charge 2/3, 1/2 spin number, baryon 1/3, 0 strain because it's not strained quark, but the charm value is +1. Okay, it's not related to bottom nets and top nets. Bottom quark has negative 1/3 charge compared to electron. Spin number 1/2, baryon number 1/3. 0 strain because it's not strained quark, and 0 charm because it's not the charm quark, it's bottom quark, right? The bottom quark, of course, will explode the +1 bottom net. Please note that this is negative 1/3 and -1 straightness, but for bottom quark, even it has negative 1/3 charge, it has +1 bottomness. Okay, and the top quark has 2/3 charge per electron. 1/2 spin number, 1/3 baryon number. Nothing related to strain net, nothing related to charm, nothing related to bottom nets, but it will express +1 to the value of top nets. All right, and that's the thing we need to know. Okay, so what happened to this?นะครับขอเช็คผมกล้องอันนี้นิดนึงครับว่าไปมาอย่างไรนะครับ All right, let's go further. That's the whole thing in this table, which is taken from the book number 2. Okay, if you go into the detail of the quark particles, you would see that. So what is the benefit of considering a strain net number, charm number, bottomness? We will consider the conservation of this number later. That's why we need to be familiar with the charm number, bottom number, top number, strain number. Okay. 2 principal categories means 2 categories are hadron. Oh, this one is nothing. We're gonna reduce hadrons which have strong interaction, and leptons which do not. Okay, hadron have strong interaction, not only quark. Okay, and leptons do not interact in the strong force. Okay, that's why the tau lepton is not classified into quark category. Okay, because it doesn't involve with strong interaction. So let's consider the light one first, leptons. What is the meaning of lepton? Lepton is the word from Greek. Okay, we borrow the word leptos from Greek. So lepton means from the Greek word small or light. Okay, it's small or light, and lepton are a group of particles that participate in the weak interaction. Okay, they don't participate in strong interaction, but rather in weak interaction. The positive electron, it's known as positron, right? This is what you may have seen before in the nuclear reaction process, right? Yeah, it is the E plus 0, 1, right? Even it's not, it doesn't have proton, but we still leave number 1 here at the lower left or the left subscript, because it seems that we have it. It's equivalent to 1 proton. Okay. You may use even the letter E or beta because it's actually a beta particle. All right. What else? The positron was discovered in 1932 by Carl D. Anderson during an investigation of cosmic rays. Okay, he was busy with cosmic ray, and he finally found the positron, okay, the antiparticle of the electron. Anderson used a cloud chamber. Okay, cloud chamber is the popular or the widely spread experimental tool, or the common experimental tool in that generation, in the early days of particle physics. Okay, in 1930, I think almost 90 years ago. Okay, and 5 years later, 2 new particles were discovered. Okay, so human is eager to explore particle. Human wants to know more information about a particle in physics, because we could understand the universe, we could predict what is going on in the future with the universe. Okay, so that we can adapt ourselves to live in the future. Okay, and that might be useful. Okay, and most of the effort was done here in the Society of Physics. These particles in 1937, right? 2 particles. These particles are known as muons. Okay, muons. They usually use the Greek letter to represent several scientific stuff, right? I don't know. Maybe you could use the Thai alphabet to represent any particle that you may find. If you want to become a physicist, or you want to study physics in the future. Okay. Yeah. The muon. That's why. What is the reason why we say muons with S with the plural version here? Because there are two particles. The first one has the negative charge. The second one has a positive charge. Okay, muon negative has a charge equal to that of the electron, and its antiparticle, which is not usually. Sometimes we use the mu with bar, right? For example, in this table, the muon has its antiparticle denoted by mu bar, right? Which is anti-muon. Because muon has -1 charge, so sometimes they use -1 at the superscript of the letter mu. But if in the same way, if you want to express muon for the antiparticle, you may leave the plus sign here. It looks like electron with E plus, which denotes a positron. Okay, in the same. But in the typical way, you have to use bar. Okay, in this standard model. But in any way, we understand that this one is the antiparticle to the negative muon. Okay, the positive muon is actually the anti-muon and has a positive charge of equal magnitude. Muons are unstable. Okay, muons are both versions of muon are unstable because the size is big. The mass of this one is big compared to electron. It's both are going to decay to become electron. Okay, usually we cannot see muon easily. You could see muon only in the accelerator, which exists in CERN. You know CERN, CERN, CERN. You can see say CERN, CERN. Okay, if you want to work in particle physics, you have to go to this. Okay, CERN or CERN. In German we would say CERN, right? But in English you may say CERN. CERN or CERN located in the border between Switzerland and France, I think. Oh, ทำไมหานานจัง What about the internet status to Russia? Okay, this is Thailand and CERN, which is the biggest place. Sorry, this is in German. Schweiz mean, this is the German word. I'm sorry for that. This is Liechtenstein. This is Switzerland. Okay, this is Switzerland. This is Belgium. This is France. This is Paris. Oh my God, what happened? CERN is the laboratory, the biggest one that has the biggest accelerator, which built up under the ground because it's too big. Okay, because it's too big, we cannot have the place that's long enough. Why they spread it out? ไปไม่ได้นะ CERN. No. Here. This is, oh no. This is the the particle accelerator. Here. They build up the. If you want to work in particle physics, you should go and apply for the job here at this laboratory because this is the biggest one and the most advanced location that tell everything to the world. Okay, this is the location where you work. Is the around the middle at the border between France and Switzerland. Here is the picture, the photo of particle accelerator. You will let the particle be accelerated. Okay, increase the speed along this tunnel, along this pipe. And what is the purpose for that? Once the particle has more acceleration, has more speed, the particle would have more kinetic energy, right? 1/2 mv squared, right? And once you use the particle with high kinetic energy, you could build up the bigger particle. And ผมก็เลยหาตำแหน่งให้คุณไม่เจอนะ เอาเพื่ออนาคตคุณนะครับ ถ้าใคร for example this one is also the place, I think this is in the United States, the particle accelerator. They build up on the ground. Okay, but CERN build up the accelerator under the ground. Okay, so that it will not disturb anyone. This one is underground. It's like the train tunnel okay, and where is that? Sand. Okay, CERN, you can see. Okay, if you look the sand from Switzerland here is the location where you work in this laboratory. It's a campus, okay, of physicists that work on particle physics, okay, which is the story we are talking right now, okay. For your future, if you fall in love with particle physics, you may be the person who discovered the bigger particle in the future. You should go here to CERN, okay, at the border between France and Switzerland, okay. Yeah, it's this one. Sorry, the name, the full name of CERN is I don't know. What is the CERN is the organization supported by United Nations or UN, right? CERN stand for นะครับไม่ได้ใช้หน้านะผมก็จะลืมครับ stand for the full name of CERN is okay. It came from a French word, so but in English it's called European Council for Nuclear Research. Okay, you need to finish your doctoral degree. Okay, you need to have PhD in physics or any kind of these and apply for the job at this location. Then you will be the leading person who work in nuclear physics and or particle physics. The actual word for then in French is something like this. Okay. Okay. What is that? นะครับพาออกข้างนอกนะครับเพื่อให้เห็นโลกกว้างนะครับเดี๋ยวจะหาว่าอยู่แต่ไหนโอเคwhere is okay here the actual full name of the word sand is the following. It came from French. Okay, I didn't study French, so I don't know. Sand comes from the word this one. Okay, it's like council. European for mean for. Okay, la mean the. Okay, researcher mean research. Nuclear, right? It's nuclear. Okay, CERN, sand, but it's ordered in French style in French, so that's why they say sand. But in English, it's known as here the full name of the sand is this one. This one. In English, we would say European Organization or Council. Okay, European Council for the Nuclear Research. If you translate one word by word or literally, European Council for the Nuclear Research. Okay, that's the meaning of CERN. The full name in English is like this. It's like the SI system. Okay, they form up from the French word. Okay, CERN is the place where they build out the biggest accelerator on Earth. I'm going to show you where is the location of CERN ครับพยายามมอบให้ทำให้คุณเห็นโลกกว้างนะครับถ้าใครชอบวิชาฟิสิกส์ตกหลุมรักฟิสิกส์ไปเลยครับเข้าไหมเรียนฟิสิกส์เลยไม่ต้องสนเรียนหมอเรียนแพทย์เรียนที่คนนิยมนะครับแล้วคุณชื่อคุณอาจจะเป็นอย่างคนที่ค้นพบฮิกส์โบซอนนะครับก็คือคนชื่อฮิกนะครับเข้าไหมเขาแก่แล้วอายุ70-80คนนั้นก็อยู่แซนเหมือนกันนะครับเข้าไหมGoogle Map where is that sand ยังไม่ไปให้ I may need to copy this one European Organization of Research นะครับมาถึงจุดนี้ผมต้องบอกคุณทั้งหมดนะครับบอกแม้เกินระดับชั้นม.ปลายไปด้วยนะครับเผื่อคุณสนใจเพราะว่าช่วงม.ปลายก็จะเป็นหัวเรียวหัวต่อนะที่จะชี้ชะตาเส้นทางสาขาอาชีพคุณครับคุณอยู่กับมันอีก30-40 ปีนะครับจนคุณเกษียณครับโอ้ no แซนโอ้ no 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 โอ้เนี่ยเจอแล้วนะครับโอเคyeah here it's sand โอเคไม่ได้พูดเล่นๆนะครับมีจริงนะครับโอเคไหม and อันนี้เป็นที่นำครับอยู่ใกล้ๆกับเมืองเกนส์นะครับโอเคมีอีเคียด้วยนะครับ this is the airport of the Genf โอเคyeah sand right here นี่นะครับเป็น accelerator นะครับ this is the particle accelerator pipe or tunnel which is built up under the ground okay it's very big and it takes very long distance so that we could have enough energy to build up or study the big nuclei if you zoom out you will see that แต่ว่าถ้าคุณจะใช้ชีวิตที่แถวนี้นะคุณเรียนภาษาฝรั่งเศสนะครับเพราะว่าเป็นบริเวณที่ใช้ภาษาฝรั่งเศสแล้วคุณจะอยู่สบายนะครับit's the border between you could see the black one here right this is the border between this is the France side this is the Switzerland side okay it locates very close to the border between France and Switzerland okay this is the location of CERN all right the biggest place where the people are doing the research in nuclear or particle physics okay yeah one of the thing of the result is the muon okay they accelerate the particle to hit something and they get muon both muon are unstable and they will finally เราต้องถึงเท่าไหร่1640นะครับผมก็ไล่ไปเรื่อยนะผมก็พาออกนอกเรื่องไปเรื่อยครับให้คุณได้เห็นนะครับเพราะว่าอายุยังน้อยนะครับอนาคตยังอีกไกลนะครับมีอันไหนดีก็บอกให้ฟังเป็นอนาคตสำหรับคุณครับอาจจะได้รับรางวัลโนเบลไพรส์ก็เป็นไปได้นะครับโอเคไหมเพราะว่าที่สุดของนักฟิสิกส์ก็คือได้รับรางวัลโนเบลไพรส์นะครับboth are ผมมัน40อัพแล้วมันหมดโอกาสแล้วนะครับเรียนวิศวะไฟฟ้าครับโอเคboth are unstable whether muon negative or muon positive which is the anti-muon both are unstable they will decay into electron with the same sign if you start from muon negative you will end up with typical electron if you start from anti-muon or mu plus you will end up with positron all right apart from electron with the same side you will get two neutrinos okay with both version neutrino and the anti-neutrino all right and the lifetime for the muon is very short okay it's microsecond okay you cannot see muon easily because it will decay rapidly it will last only 2.2 microsecond. The process of the muon could be written in the detail as equation 111. We start from the rest muon negative, for example, we will get electron and we get electron neutrino, we get electron anti-neutrino, okay, as the outcome. And now we move to the bigger one, okay. We arrive at muon, right, and the anti-muon, muon plus. Now we move to tau. Okay, you have seen many things about electron already, right? We have discussed many things about electron. We will move to tau lepton. Okay, the bigger version, which has mass approximately 1.8 giga electron volt per c square, and yeah, it has its own antiparallel. It's known as anti-tau, and the mass has the same size. Charge are opposite to each other. Charges are opposite to each other. Spin numbers are the same, 1/2, 1/2, and yeah, the mass is very big. So let's talk about tau lepton. Tau lepton was discovered in 1975. With high probability, the discovery is done in sand. Okay, I'm not sure. As the mass of 1784, which is very close to this one, right? เดี๋ยวเปิด2 อันแล้วกันครับรูดไปรูดมาเดี๋ยวคุณงงครับ Okay, in this table they say 1.77, right? Is giga electron volt. So this one 1000 giga too. It's 1.784. It's very similar, right? Because this one say approximation, right? Approximate to be this value. So it's reasonable, right? Okay, 1000 is 1.7 giga electron volt per c square. Okay, about twice that of the proton. Okay, the mass of this one is about twice of that proton. Let's take a look at the mass of the proton at the beginning of this chapter. Where is that? Okay, here. Mass of proton in atomic mass units. Oh, we don't have the value in mega electron volt. We don't have that. Sorry for that. So no problem. Somewhere here. Okay. Yes, the mass of the tau lepton is about twice that of proton, but they are not considered as the quark or something like that at all. The tau are more massive than the nucleons, and tau are also unstable. It's like a muon, right? Whether the typical version or the antiparticle version, both are unstable, and a tau could decay into muon plus 2 neutrinos. Okay, you could see that before it turns down to it goes down to electron, they need to become first the muon, okay, and then it will go down or decay to electron because tau is much bigger than electron. The process of the tau will be discussed later. However, they are classified as lepton rather than baryons. Okay, they are not baryons because they have no strong interaction. Okay, they do not involve with the strong interaction in the strong force. There is strong indirect evidence that the electron neutrino has a non-zero mass, right? We have discussed it before about the mass of the electron neutrino or electron antineutrino, right? It's people believe that the electron neutrino or electron antineutrino has the mass of 0, but it's not the case because someone has confirmed that the mass of electron neutrino is not 0 at all, but it's still unknown because it's very, very light, and electron neutrino doesn't involve with anything because it's neutral, it has no charge, it's very hard to detect. It's still in a question. If you actually go to the final part of this chapter, there are many open questions to this story which might need some effort from the human to do the research, to deliver the answer, right? Okay, all leptons have spin 1/2. Of course, here you could see that all leptons have spin 1/2. All right. Every green particles, every green particle has the spin number 1/2. You could see here the third one, 1/2, 1/2, 1/2, 1/2. All these 12 particles have the spin number of 1/2 or 1/2. Okay, 1/2 as spin number. Now we move to the next table for the leptons. Okay, we go into the detail of the lepton on this this table. Okay, lepton is right here, 12 particle, right? So we have somehow 1, 2, 3, 4, 5, 6, and the antiparticle 6, 1 here, right? So the total number of particles in leptons is 12, as same as this one. Okay, but in this table they don't provide a value of electron lepton number, muon lepton number, tau lepton number, which will be used later in the conservation rule. All right, let's take a look at electron. Electron has a mass of 0.511. Okay, the same value here, and the number of electron lepton number is +1 for both electron and positron. Lifetime is stable. Okay, they will remain as this form later. Okay, in the electron neutrino, which is denoted by nu e, and its antiparticle, this one, electron antineutrino, will be also a stable particle. The electron lepton number will be designated by 1, 2. The mass is very, very light. Okay, less than 3 eV, and muon, right? Muon minus, muon plus, which is the antiparticle to the typical muon. Mass of muon is around 105.66 or 105.7. It has no electron lepton number, but it has muon lepton number. We don't pay attention to the tau lepton number because this is muon. The lifetime is not stable particle. Okay, it's going to fall down or decay into something else. Okay, it will last only 2.2 microseconds, and it will decay into electron neutrino, electron antineutrino. What about muon neutrino, which is this one? Muon neutrino and muon antineutrino. The mass is less than 0.19 mega electron volt, 0.17, okay, close to each other. The mu lepton number is +1. It's stable. Okay, both will not decay to any other particle. Okay, and because this has no charge, okay, it's neutral, they are gonna be stable. And let's take a look at tau particle. We have tau in the negative way, and for the antiparticle it's going to be positive tau, right? They denoted by tau minus and tau plus. Mass of the tau is approximately 1.77 giga electron volt, or is in terms of mega electron 1000. Okay, very close to each other. And the tau lepton number is +1. It has no value for electron lepton number, muon lepton number. The lifetime is even shorter than the muon. I don't know, it's 29 picosecond, right? It's going to decay to muon minus or muon plus. It depends on the initial version of what you have. Muon negative, muon muon antineutrino, muon tau, tau antineutrino, and electron antineutrino, and tau neutrino, right? And regarding the neutrino for the tau, okay, the mass is 18.2, okay, exactly the same value. It has tau lepton number as +1, and it's stable. Okay, it's stable. All right, that's the tau lepton particle that interact through the strong force. Okay, we don't have the equation for tau decay. Particles that interact through the strong force are known as. Now we move to the next type of particles apart from the elementary particles. In this table, we see the bigger particle that the human has discovered. Particles that interact through the strong force are called hadron. Hadrons are much more complicated than leptons, and hadrons are distinguished by, classified by the masses or spin numbers. And once we use this criteria, we have two types. The first one is called meson, which is the lighter one. The heavier one is known as baryons. Okay, the story about hadron or meson, the story about meson start in 1935. It starts from the Japanese physicist whose name is Hideki Yukawa. His lifetime is 1907 to 1981. He proposed a hypothetical particle. He believed that should be this particle. He called this particle as meson. Okay, the light one first. With the mass between electron and proton. Okay, it's halfway in the middle between electron and the proton. But at that time, he didn't have any experimental result to verify his belief on his hypothesis. Yeah, once he proposed this possible idea in 1947, another family of unstable particles was discovered. These were called pi meson or pions. Right? They use again the Greek letters. It's a meson, but it's pi. Okay, so simply speaking, we say pions. Okay, pion have charges and even no charge. Okay, version. There are three versions of the pions. The first one is the negative charge version, which is pion minus. Okay, and the positive charge, the same as electron, is called pion plus, and pion without any charge at all is called pion zero. Okay, pion do interact strongly with nuclei. They are the particle predicted by Yukawa. Okay, so someone confirmed the idea by Hideki Yukawa as mediators of the nuclear force. The meson have some property like this. The spin number is 0 or 1. Meson are known to decay finally into electron and positron, so it's a big version to electron and positron. Neutrinos and photons, okay, not only electron, positron, but also neutrino and photon. The pion negative, the minus pion, could be decomposed into muon, right? You know muon before, right? Muon is right here, okay, which is a kind of lepton. Pion minus is decomposed, minus pion or negative pion is decomposed into negative muon plus the neutrino muon. Okay, and a good example of the meson is the pion. This is the lightest of the known meson. So now let's move to the baryons, which is the bigger version of the hadron. Okay, the bigger particle to hadron. Where's that? Baryon have masses equal to or greater than the proton mass. Okay, the name baryons means heavy in Greek. Okay, the word is derived again from the Greek. น่าจะหมดเวลาแล้วนะครับโอเค40 นาทีให้15:40นะครับให้คุณนภัสนะครับโอเค we have to finish our classroom right now for M605 if any of you has a question just let me know raise the question to me in any communication channel and if not then see you on Friday, right? We don't have homework, I think, in this week because it's only the explanation to several things in particle physics. There is no computation problem at all. โอเคครับสวัสดีครับบ๊ายบายครับพบกันวันศุกร์ตอนเช้านะครับแล้วก็รู้สึกว่าศุกร์ครั้งที่2ศุกร์คาบ2คาบก่อนเที่ยงนะครับอาจารย์ณัฐพงศ์ครับเขาจะมาสอนแมทเหมือนเดิมนะครับโอเคไหมเขาจะใช้คาบ4ของคุณเราจะพบกันแค่คาบ3นะครับ See you on Friday บ๊ายบายครับสวัสดีครับThe next one is this one is M605 right in Wittayalai School page oh here oh I didn't see you in Zoom no one in Zoom it's from right yes Electron Neutrinoธนกรปินธรรมวาเลนเทรนภาพวินก่อน we will send it through to that my group what yeah nothing wrong let's send it proton right here it's somewhere here M605 bar 02 2022 it's there alert spotter. And in download. This is M605 and good note. This yes, there's nothing more in this machine. This machine. Okay, so essentially but not 21 from that's the OBS and here is the reason not one. Oh no. Okay, machine. Wait, let me one again. Let me one. And two. What? Go. One. 3 note pop. Here we have first so this now Suankularb from quick tap pop. And let's into oh no, that's M604. And now we finish. Stop the soul. Then and this one. Stop. Finish. Stop it already. Yes. Close the microphone.